In this video, we explore the de Broglie model for the electron. In 1924, Louis de Broglie proposed a new speculative hypothesis: electrons and other particles of matter can behave like waves. As it can be seen, it was a very revolutionary idea for a PhD thesis. But this idea, although new, has its basis on the Bohr's model of the hydrogen atom. In the Bohr atomic model, the electrons could move only in allowed orbits. Also, this model proposed that the angular momentum to be quantized. But there was no justification for the former. De Broglie used the idea of the allowed orbits, but assuming that electrons are waves that can fit on such allowed orbits. We can remember that the oscillation modes in strings are defined by the number of nodes that can be counted on a cavity. Actually, this idea can be extrapolated to the circular orbits of the electrons in the Bohr atom. These are the first 5 modes of oscillation in strings as well as their circular counterpart. However, the condition for the electron to fit in an orbit was that such an orbit should behave as a cavity, meaning that only wavelengths that can fit in integer numbers could exist. Meaning that the length of the orbit must be an integer multiple of the wavelength. Let's calculate what is the wavelength of a wave that can fit in the orbit. Using the Planck's definition of energy, and the classical definition of the kinetic energy of the electron. Combining these equations, we can see the following. As the mass is the same in both sides of the equation, and knowing that the classical momentum is simply the product of the mass times the speed, then we get. This is called the de Broglie wavelength, and refers to the wave behavior of the particle. More important is to note that due to the use of the classical momentum to get this wavelength, then we can apply it to any object. Let's solve an example to see what is the magnitude of de Broglie wavelength for a common system. Example 16. Determine the de Broglie wavelength of a person running at 10 km per hour. Suppose the mass of this person is 70 kilograms. Could you solve it? Answer. We know that the de Broglie wavelength is defined as follows. Using the classical definition of the momentum, we see that. Using the values we have, then we can see that the de Broglie wavelength is the following. It is possible to see that this value is very small. Actually, it is 26 orders of magnitude smaller than the Bohr radius, and 24 orders of magnitude smaller than the shortest electromagnetic wavelength. Actually, we can see that the value of the de Broglie wavelength is in general very small. It is so small that it could be impossible to observe it. Furthermore, every macroscopic object has an associated wave behavior, but its wavelength is so small that it is imperceptible, even for the most sophisticated instruments. On the other hand, it is possible to demonstrate that the quantized angular momentum that Bohr proposed in his atomic model is easily obtained with the de Broglie proposal. For example, if we consider that the classical momentum in the de Broglie wavelength and the integer wavelengths in the circular orbit condition, then we have the following. Finally, considering the classical definition of the angular momentum, then we get the quantized angular momentum, as proposed by Bohr. Although de Broglie proposal was totally out of the mindset of people at the beginning of the 20th century, it proved to be another of the key discoveries during the modern physics revolution. Actually, this discovery is considered as the beginning of a new research area called the wave mechanics that opened a new venue for the quantum mechanics. In a future video we will study a complementary theory to de Broglie model, proposed by Erwin Schrödinger. Stay tuned.